Welcome. Today we will explore how we architect AI networks to withstand failures. In massive AI training clusters, a single link failure can halt a job running on thousands of GPUs. We will look at specific topologies and protocols designed to ensure high availability and continuous operation. AI environment, high availability means more than just having a backup cable. Because AI workloads are tightly coupled and bursty, a failure that causes packet loss or high latency can ruin a training run. We design fabrics that are self-healing, meaning the network can instantly route around a failed link to maintain the flow of data. We approach this in layers. Ensuring the physical topology has multiple paths, the control plane has backup managers. The protocols support active-active forwarding. This flowchart illustrates the impact of network design on AI jobs. On the left path, a standard network suffers a link failure leading to a job stall or failure. On the right, an AI high-availability network uses self-healing mechanisms. When the link fails, the fabric automatically reroutes traffic, allowing the expensive training job to continue without restarting. Unique aspect of AI networking is the rail-optimized topology. Instead of connecting a server to just two switches for simple failover, we connect specific GPUs to specific leaf switches, creating parallel rails. If a switch in rail 1 fails, we don't lose the server, we only lose the bandwidth of that one rail. The job can often continue at a reduced speed, which is preferable to a hard stop. Architecture isolates traffic and ensures that a single hardware failure has a limited impact on the overall cluster performance. Here we see a rail-optimized design. GPU 1 connects exclusively to leaf switch 1 in the green rail 1 fabric. GPU 2 connects to leaf switch 2 in the rail 2 fabric. If leaf switch 2 fails indicated by the dashed box, GPU 2 loses connectivity, but GPU 1 and rail 1 remain perfectly operational. This independence allows the system to maintain partial throughput during failures. High-performance InfiniBand fabric, the subnet manager or SM, is the brain of the network. If the SM goes down, the network cannot adapt to changes. To mitigate this, we deploy SM high availability. This involves a master node and one or more standby nodes. The standby nodes constantly synchronize with the master. If the master fails, a standby immediately promotes itself to master, ensuring the fabric remains manageable and operational without disruption. We often manage this cluster via a single virtual IP. This sequence shows the SMHA process. Initially, the master SM syncs its database to the standby SM while configuring the fabric. When a failure occurs at the master, the standby detects it, promotes itself to master, and resumes control of the fabric. The administrator continues access seamlessly using the virtual IP VIP, which now points to the new master. InfiniBand handles the heavy compute load. Ethernet often manages storage and cluster management. For these networks, we use multi-chassis link aggregation or MLAG. This allows a server to connect to two separate switches simultaneously, providing active-active layer 2 redundancy. At layer 3, we use virtual router redundancy or VRR. Unlike legacy VRRP, VRR allows both switches to actively route traffic and respond to gateway requests. This combination ensures that the critical plumbing of the data center storage and management is as robust as the compute fabric. This diagram illustrates Ethernet redundancy. The server at the top uses a bond to connect to both switch 1 and switch 2 via link A and link B. These switches are peered using MLAG. At the bottom, they share a virtual gateway IP 10.0.0.1 using VRR. This setup ensures that if link or switch 1 fails, traffic instantly flows through link B and switch 2 without severing the connection.